but I kept it until today. So let's go over that real quick. Make sure that you follow what we're saying, because there's going to be a couple of questions on the second exam on this. It's called the inverse square law of light. So what does that even mean? Inverse square law of light. What is the inverse of something, right? So inverse of something means 1 over that something. So inverse of 2 is 1/2. Inverse of 5 is 1/5, like that. So what about inverse square of 2? That's 1/2 times 1/2. Inverse square of 2. What about inverse square of 5? That's 1/5 times 1/5. So inverse of 5 is 1/5. Inverse square means 1/5 times 1/5, like that. Any questions here? All right, excellent. Now we have a bunch of candles here from here to infinity. So when we look at the closer candle, we see it's really bright. And it gets fainter and fainter and fainter and fainter and fainter as we go towards infinity. Now, believe it or not, by looking at the candle, you can tell how far away these candles are. But you have to measure the distance to the first candle first. So if you know the distance to the first candle, you can measure the distance to all the candles in this picture. You just have to figure out how much fainter they are. Same with the galaxies, same with everything else, same with these rulers. Now, believe it or not, this is the only way we can tell distances in the entire universe. That's it. There's no other way. This is it. And there's drawbacks too. So let's see what this is all means to us. This is a light. So if you look at this light, as the light propagates, as it moves, it spreads, right? So as it spreads, if it's 1 foot away, it lights up this one little square here. At 2 feet, it becomes 4 times bigger, not twice as big. So how does that work? Why does it become 4 times bigger, but not twice as big? This is something I got to show you guys. So let me show you this real fast. And this has to do with this flashlight that I got here. I got Cops flashlight, the big one. So here I have, let's see, I have a circle here. You can see the circle. This circle is from 1 foot away. So if I increase the distance, the circle is going to become twice as big. Like that big, right? Okay, so it's just twice as big. Then why is it 4 times less light? Because the area that you're spreading this light is 4 times bigger. How do I know? It's because the area of a circle is pi r squared. It's the square of the radius, right? Radius, same, it's like twice the radius is diameter. So if the diameter becomes twice as big, the area that you're spreading the light is going to become 4 times bigger, not twice as big. So if I go from 1 foot to 2 foot, this is twice as big, but it's 4 times the light. Now the light here doesn't change, it's the same light. I'm spreading it over a much bigger area. So if I go 3 feet away, no, it's a lot fainter, you see? It's a lot bigger, I'm spreading the same light. So again, closer. This is not twice as bright, this is 4 times brighter. This is twice as close, it's 4 times brighter. So that's what it means. That's the inverse square law of light. But for this to work, you have to look for the same objects. Like if you find something close by, let's say 1,000 light years away, that's nothing, it's pretty far, but it takes 1,000 light years for the light to get here. But 1,000 light years is very, very close when we compare it to billions of light years, right? So that's the only way we can find distances to the edge of space and time. That's the only way. There's no other way. All right, so now I made some little videos, actually some pictures.
Can I just clarify that?
Yes, of course.
So are you saying that as light gets farther, the size of it gets bigger?
Yeah, there's a cone of light, so as the light moves, it spreads, right? As it spreads, it becomes a much bigger area, right? It covers a much bigger area. That area becomes twice as big if it's twice as far. But the area that you're covering is 4 times bigger. That's what the deal is. So the deal is inverse square, right? So if I go 1 foot away, I'm covering up this much area. But then the same light is spreading now over 4 times the area of this guy at 2 feet. So this isn't twice as faint. This is going to be 4 times less light here. When you go 3 times farther, now you have 9 times the area to cover. So it's going to become 9 times fainter, like that. That's what.
And the light is covering that whole.
Yeah, it's just the amount of light decreases as it moves, right? Because it spreads.
Sure.
All right, so let's take a look here. So we have 2 BMWs. I made sure I brought you guys BMWs here. And these BMWs are 325i, okay, just in case if you're wondering. So there's a guy here from Fortnite. So this guy from Fortnite, yeah, Linda doesn't know what Fortnite is, do you, Linda?
Yeah, I have a teenage son.
Oh, you do know Fortnite. Yeah, I have no idea what Fortnite is. I just know that this guy is from Fortnite. So this is the observer, right? The observer is looking at these BMWs. This BMW is car number 1, is 1 mile away. Now, they're identical BMWs, same headlights, same everything. Now, this second BMW is 4 miles away. So how many times farther is car number 2 than car number 1? Well, car number 1 is 1 mile away. Car number 2 is 4 miles away. So 4 divided by 1, 4 times farther. So if it's 4 times farther, we say inverse square of 4 is 1/4. Inverse square of 4 is 1/4 times 1/4. That's 1/16 the light. Or you can say it's 6 times fainter. So you can say 1/16 the light or 16 times fainter. So this light here is 16 times fainter than this light here. All right, now we're going to move the cars. So now we have one car at 3 miles away, one car is 1 mile away. So this car didn't move, car number 2 moved. Now how much fainter does the headlight of car number 2 appear to our observer? This is 3 miles away. Now we say it's inverse square of 3. 3 divided by 1 is 3 times farther. So that'd be 1/3 times 1/3, 1/9 the light, or 9 times fainter, like that. All right, so let's see if we can get this into astronomy now. And I have a young girl with a telescope looking at this object number 1. Now, you can figure out things that are really close. And the way you do it is by looking to see how much stuff that you're looking at is wiggling when the Earth goes around the sun. So you look at, let's say, a star from someplace in the Earth's orbit, let's say in this first day of spring, and you notice the position of a star. 6 months later, you look at the same object, you can see his position has changed a tiny bit. That positional change tells you how far away things are very accurately. It's kind of like putting your finger in front of your eyes, and then if you close one eye and open the other one, and do the same thing with the other eye, continuously opening and closing one eye, you can see your fingers moving back and forth. The farther your finger, the less it's going to move. By how much the finger is moving, you can figure out the distance to the finger. Same thing with the stars. You can figure out distances to stars, something called parallax. Now, the one that I'm showing you here, the star was found to be 10 light years away by very accurate measuring this parallax of the star. So we know object number 1 is 10 light years away. Now we see an identical object. It's the same exact type of star, but it's 9 times fainter. So if it's 9 times fainter, we say object 1 and 2 are identical objects. Object 1 is 10 light years away, Object 2 is 9 times fainter. Question is, how far away is object 2? Identical objects. So if it's 9 times fainter, how many times farther must it be to be 9 times fainter? It must be
3 light years?
3 times, no, it's 3 times farther, not 3 light years, but it's 3 times farther. So how do you figure this out? Very easy. You say object number 2 is 9 times fainter. Then you get the square root of 9. That gives you 3. So it's 3 times farther because it's 9 times fainter. And if that's the case, then 3 times 10 light years is 30 light years away. So that's how you figure things out like that. All right, so now, let's say it wasn't 9 times fainter, but it was, let's see, 25 times fainter. How far away is this guy if it's 25 times fainter?
5 times farther away.
50 light years?
50 light years, that's right, 50 light years. Now, I don't know who to give the point to now. 2 people, I think, talked. Or was it the same person?
Kelsey and I think Linda.
Kelsey, what's your last name, Kelsey?
Miller?
I'm sorry?
Miller?
Miller. Thank you, Kelsey.
It was Cindy, but I said 5, not 50.
I'm sorry?
It was Cindy Costa talking, but I did not say it correct. I said 5, not 50.
Oh, yes, 5 times. So
Yeah,
now, what is 100 times fainter? Now, how far away is this object?
10 times? 50 light or 100 light years away?
100 light years, that's right. So if it's 100 times fainter, that'll be the square root of 100, or 10 times farther to be 100 times fainter. If this guy is 10 light years away, then this guy must be 10 times 10 or 100 light years away. There'll be 2 questions on this on the second exam. So please try to, figure this out by yourself. Look at this video again if you didn't figure it out already, and then try to figure this out. All right, let me give you one last example. Say now this object is 10,000 times fainter, because it turns out to be really, really far away. Now, how far away is this object? It was 10,000 times fainter.
100.
How far away is it if it's 10,000 times fainter?
100 times farther.
1,000?
1,000 light,
Right. This is
1,000 light years away.
that's right. This is 10 light years. The other one is 100 times that. 100 times 10 is 1,000. No, all right, like that. All right. So Linda gets the point, I guess. All right. Anybody have any difficulty with this? If you have any kind of difficulty, with anything, you guys, you just come to the office, right? Just come to the office for anything. I'm just sitting there waiting for you guys, making these stupid little, slides for you and videos and stuff for you. So I'm available on Wednesdays.
If we were measuring, I initially thought we were measuring the distance from the first to the second star, but we're not. We're measuring the distance from us. If we
Well, it's the same thing. If this one is 10 light years away, you just subtract it from the distance of the second star. So if the second star is 50 light years away, and this one is 10 light years, second star will be 40 light years away from the first star. So yeah, this is the way we figured out how big the universe is. Otherwise, how are you going to figure it out? But there's problems with this. One of the problems is there's garbage in the universe. Yeah, there's not just garbage in our oceans, there's garbage in the universe. So there's dust, there is gas, there's all kinds of garbage between us and the end of the universe, right? The edge of the space and time. So you got to figure that out. You got to go, okay, so how much garbage is this way? How much garbage is that way? How do you figure out how much garbage there is? You take a look at the light. See if there's any absorption lines in the spectrum of whatever heck you're looking at. So one of the things is that you have to get the distance to the first object. And the second object has got to be exactly the same kind of object. We call these kind of objects standard candles. So if you ever hear standard candle, that's what they are. One of the standard candles is something called supernova type 1a. Awesome. That's how we know how big the universe is through supernova type 1a. In fact, we also know that the expansion of the universe is accelerating. Dark energy. The only reason for that is, again, same exact type of thing that I did for you there. The guy did it and he got a Nobel Prize for it. That's how they figured out there's dark energy in the universe. We'll get to that later, but this is just the way you do it. All right, now let's get to the good stuff. So this is going to lead us to the evolution of the stars, something called stellar evolution. So what happens to the stars once they get old? You know, like the sun is not going to just die; it's going to die a strange kind of death. So that's what we're going to do. We're going to also look at black holes. That's the end of a very massive stars. When they die, they go black hole. All right, so two things we got to know for sure. One is called luminosity, total energy output per second in all directions. You look at the sun. Okay, the sun has got a whole bunch of size, a sphere, right? So there's light coming towards us. There's light moving away from us. There's light going to the sides. There's light going this way. So if you can have like a special magical net, you put this special magical net over the sun, you measure how many photons are coming out every second. That's the luminosity of the sun. So the luminosity of this flashlight is how much light is coming out of this baby every second. That's the luminosity of this flashlight. Now, brightness is also important. Brightness means how much light is coming out per square inch of the sun. So you figure out how much light is coming out per square inch, and that's called brightness. So let's see, I have two flashlights. You can tell this just by looking, you can tell. Here's one flashlight, here's a second flashlight. Okay, which one is more luminous? This one. This one is not as luminous. Why isn't it as luminous? Because this one is smaller. It's also not as bright. So things that are really, really hot are really, really bright. We say surface temperature of the stars determines their brightness. So if a star that is 10,000 degrees, it's going to be brighter than a star that is 2,000 degrees, like that. Now there's something called spectral class. We classify stars according to their surface temperature, and that was the O, B, fine girl, and kiss me stuff. So the spectral class is based on surface temperature. So brightness, surface temperature, spectral class, they're all the same things for a star. Whereas luminosity is all the energy coming out. All right. Okay, so luminosity of a star depends on two factors. If two stars have the same surface temperature, so they're both 4,000 degrees, let's say, the one that is bigger is more luminous. It's like a flashlight. The cop's flashlight is a lot more luminous than a little tiny flashlight that you keep on your keychain. It's obvious because the cop's flashlight is so much bigger, right? The opening so much bigger. So a star that is bigger is going to be more luminous. Their brightness is the same. They're both the same temperature. So brightness, identical. The one that is bigger, more luminous. Now we have two stars that are exactly the same size, but one of them is hotter. One of them is 12,000 degrees, one of them is 4,000. Which one is more luminous? The one that is hotter, the one that has a higher surface temperature, that one is more luminous. So surface temperature and size. That's how you determine luminosity. You know that's going to be one of the questions. So what makes something luminous? Surface area and surface temperature. All right. Well, that brings us to this. This is the most important diagram in all of astronomy. It's kind of like to a chemist, you know, that look at the elements, you know, the periodic table. This is like the periodic table of astronomy, right? And it was made by two guys in 1920s. One of them is Mr. H. Hertzsprung. Mr. Hertzsprung, his first name is Enjar, E-N-J-A-R, Enjar. Enjar Hertzsprung. And this guy is Mr. Russell. So we call this the Hertzsprung-Russell diagram, or H and R diagram. So this is H and R diagram. So H and R diagram is a diagram of luminosity of the stars versus their surface temperature. And they had no idea what they're going to come up with. They weren't working together. Eventually they did. But they both came up with the same answer. When they plotted the position of temperature of a star versus its luminosity, it turned out they all fit in a line like this, a beautiful line like this. And they call it the main sequence of the stars. Now, who are all these stars, the main sequence of the stars? These are stars that are normal stars, just regular stars. Stars that have not evolved yet, stars that are burning hydrogen into helium, normal stars. When you compare to people, I'd say you're all normal people, regular people. You breathe, you look pretty normal to me. Who's not normal? Wolfman, Dracula. Let's see. Anybody wants to chime in? Somebody that is not normal. Zombie. Zombies are not normal. They're dead, right?
Frankenstein.
Frankenstein. There you go. Frankenstein. Yeah, Frankenstein. Those are not normal people. So these guys are normal stars. Then we have the dwarfs here, giants, supergiant. These are freakazoids. These are the result of the evolution of the stars. Like the sun is going to become a giant star. And then it's going to become a white dwarf here. So these are the, what do you call it? Not normal. The Draculas are the starry world. These are the normal stars in the starry world. Okay, like that. All right, now they plot this in a way different ways, man. I've seen at least a couple of dozen ways they plot it. But here, there is a little hump here, actually. It's not a straight line. There's a little hump. The hump happens in the A stars. Something weird happens in the A stars. Now, remember surface temperature here? We call the surface temperature also spectral class. Spectral class will be your O's and your B's and O, B, fine girl, and kiss me. And they're based on surface temperature. So the ones that are like 30,000 degrees Kelvin, O stars. If you're 10,000 degrees, you're a B star. 8,000 degrees, 9,000 degrees, A star. Then like 8,000 degrees, this is wrong, by the way. You're F star. So the sun is a G star. The sun is over here. There's a sun is a G star. Somebody goofed this, by the way. So these are the K stars and M stars. So it gets cooler and cooler as you go to the right here. These are the coolest stars in the universe. And they're little tiny things. Now, this is luminosity. This is 1/10,000th as luminous as the sun. These guys are 1,000,000 times, some of them are actually 5-6 million times more luminous than the sun. Imagine having 6 million suns in the sky simultaneously. Like the whole sky is covered with the sun, not just one sun, 1,000,000 suns. Then they'll be as luminous as one of these guys here. That's how luminous these guys are. So if you lived in one of these solar systems with one of the suns was like this, you need to be really, really, really far away, right? How much farther? 1,000 times farther. Remember inverse square law of light? So if you're 1,000 times farther from its sun, then it'd be 1,000,000 times less light. So instead of 93 million miles away, you need to be 93 billion miles away from the sun. really, really far away. Otherwise, if this sun existed where our sun is, you just walk out of your house for 1 second, you'd be burnt into a crisp. It'd be incredibly hot. So these are all the normal guys, normal stars, right? Main sequence of the stars. So you can kind of see tiny little guys. Sun is small actually. And then these guys will evolve into subgiants, giants. Well, supergiants actually come from the evolution of these guys here. Sun-type stars, they evolve into giants. These big guys, O stars and stuff, they go into supergiants. So that's the evolution of the sun. Now, here's how the sun is going to evolve. This is what we're going to be talking about next week. So the sun first is going to become less luminous. I'll explain to you exactly why. This is the core of the sun as it evolves. It finishes its hydrogen burning, but helium that it leaves behind, it needs to burn before it becomes super bright. So it starts burning the hydrogen in its shell, then it becomes a subgiant. Then it starts burning here, it starts burning helium, becomes a real giant. And eventually it's going to become a white dwarf. So that's the evolution. Now, for now, let's get this thing on the road here. Let me get my camera. You guys get your notebooks ready. I'm going to give you guys the diagram itself. We're going to draw this together. Okay, so remember, this is the diagram of luminosity, how much light you put out versus how hot you are. It turns out it tells us a lot. It also tells us about masses. It tells us about ages, how long do they last, everything. There's a lot to learn from this diagram. So let me see, is this good enough? Yeah, looks perfect. All right. So up and down, luminosity. Luminosity. How much light output you have. So here we're going to put in 1. Now 1 stands for the sun's luminosity. So you're comparing all the stars in the sky to the sun. Because you can see the sun, you know how much light the sun puts out. So we're going to compare everything to the sun. Now the sun is a circle with a dot. It looks a lot like the sign for Target, right? Like this. The sun. That's the symbol of the sun. All right, there's the sun. So we're going to say 1 times the luminosity of the sun. So 1 times the luminosity of the sun. Then 1/100th as luminous as the sun. 1/10,000th as luminous as the sun. 100 times more luminous. 10,000 times more luminous. 1,000,000 times more luminous. There you go. Now, you couldn't put all the numbers here. This is called logarithmic. This is 10 to the power of 2, 10 to the power of 4, 10 to the power of 6, like this. So this is 100th, right? It's 100 times less, 10,000 times less. Otherwise, how could you fit all this stuff in? From 1/10,000 to 1,000,000, that's 10 billion. So I couldn't put 10 billion numbers up and down. That's why this is called logarithmic. So it's 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, like that. All right, so that's luminosity. Now here is surface temperature. Let's call this baby surface temperature, and that's called spectral class. So spectral class is surface temperature. It's based on surface temperature. Based on surface temperature. All right, so what do we got? We got the O's. O, B, a, fine girl, kiss me. Oh, be a fine girl and kiss me. Like that. So the hottest stars are something like 50,000 degree temperature. That's as hot as you get. 50,000 degrees Kelvin. That's as hot as it gets. So this is the hottest stars over here. Nobody's even seen one of these. And then here we have the coolest. It's about 2,500 degrees Kelvin. This is the surface temperature. Surface temperature also determines color too. If you're really, really hot, it'd be blue. Really, really cool, it'd be red. All right, so I'll do all that for you. These are called spectral classes. Now, they can't all stars cannot be exactly the same temperature. So we have subclasses too. Subclasses go like this. You go O0 is the hottest of all these stars in the entire sky. O0. Then O1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you got O1, O1, 2, 3, 7, 8, 9. Instead of 10, we have B0. Then B1, 2, 3, 4, 5, 6, 7, 8, 9. B9 is the coolest of all the B stars. A0 is the hottest of all the A stars. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the coolest of all the A stars. So you keep going here. This is G0. The sun is a G2 star. M9 will be the coolest of all the stars in the sky. O0 would be the hottest star in the entire sky. So it gets cooler this way, it gets hotter this way, it gets more luminous this way. This is the most luminous. This is the least luminous. So it goes like this, it goes up this way to the most luminous. All right, so what happens when we draw all these? Well, we start with the sun. Why do we do with the sun? Because we have 1 and G2. So we're gonna have to put a dot here someplace. So I go here. So that represents the sun. That one little dot. All right, let me get to the colors now. These are the red guys. M stars are red in color. K stars are orange in color. B stars are yellow in color. So we're calling the sun yellow. F stars are yellow-white. A stars are white. B stars are blue. O stars are also blue. So the colors the stars have in nature, that's it. Just blue, white, yellow, orange, and red. That's all the colors in nature. Okay, let's plot them all. So 1/10,000 will be the M9s. I'll put a dot right here. There's an M9. Dot, 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 question. Dot, 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 dot. Like that. There you go. There you have it. So all the stars in the sky that are alive, they fit within this beautiful pattern here. That's it. We call this beautiful pattern the main sequence of stars. So main sequence, and the sun is going to be right here. Okay. Now, you use this diagram to classify the stars. And you can also show the evolution of the stars. You can show everything about the stars in this diagram. So now let's classify some of these stars. So how do you classify something? Well, normal stars, like the main sequence stars, they're given something called the luminosity classes. Normal stars, luminosity class 5. Supergiants, luminosity class 1. Bright giants, luminosity class 2. Giants, luminosity class 3. Subgiants, luminosity class 4. Main sequence, luminosity class 5. So we said luminosity class is Greek number 5. So it's a Greek numeral 5. These are all Greek numeral 5s. So these are all Greek numeral 5s, every one of them. All the supergiants are 1. Students mostly have difficulty with the luminosity class. Everything else is very simple. So luminosity class is something that is forced upon us. That's just the way it is. So we say this is luminosity class is 5. All right, so let me classify them. On the second exam, we're going to have like 5 questions where you get to classify the stars according to the scheme that we have here. So let's classify this star right here. The way you classify it, you go down like this. You go down. Let's see. So the exam, you just use a sheet of paper like that. Go down. And you see it says B7. So this is B7. And luminosity class is 5. So this is B75. That's B75. So what about the sun? You do the same thing with the sun. Sheesh, man. Now I gotta move my sun. So the sun is a G25. A G25. That's the sun. So what about this guy here? What is that guy? So you can classify that guy. Can you guys hear this guy cutting the grass?
Yeah, I thought it was a drone at first, but
No, it's here. Some guy's cutting the grass.
so is that K 7 or 8, 5?
Excellent. That's right. So this is like K. And you said K7, K5, so it'll be K7.5. That's also allowed. So K7.55. Like that. Excellent. All right, so Linda gets a point. Okay, how about this one?
A
I'm sorry?
A85.
A85. Right. All right, so when we get to, like subgiants would be a 4. Giants would be a 3. Supergiants will be a 1. So it could be a 1, 3. Like that. That'll be a giant star that is temperature is like an A star, like that. We'll get to that. Okay, I'm crazy out here. Okay. Is there any questions that you guys might have about this?
Yes.
Okay.
So the vertical line luminosity, what does that have to do with the 5 class?
What does that have to do with what? I'm sorry?
The 5 class, the luminosity class 5, because there are all these other numbers over here on the vertical. I mean,
Again, one more time. All the main sequence stars are given a luminosity class. They all belong to luminosity class 5. They asked me why, because some ancient astronomer said so.
Okay.
Yeah, that's so.
But
Yeah.
what does that have to do with the vertical line of, 1,000,000, 10,000, 100, 1?
What does that have to do with luminosity? Well, the giant stars are much more luminous because they're so much bigger. Supergiants are even more luminous than that. They're so much bigger. Like that.
But you placed our examples, at different places.
Yeah, I can't even hear you anymore. I'm
You
sorry.
can't hear me? Wow.
Just barely.
Oh.
This guy's going with a vengeance. I don't know what the hell he's cutting. So luminosity classes have nothing to do with the actual luminosity. They're
Okay.
classes.
Okay.
Like, let's say luxury tax has nothing to do with luxury. It has to do, have you ever heard of luxury tax?
Yes.
Yeah? Oh, good. Luxury tax is for basketball teams. Like when they go over a certain amount of, payroll, they have to pay taxes to NBA, like that. Has nothing to do with actual taxes. It's called luxury tax. Kind of like that. So we say luminosity classes are kind of like this. Let me show you. I'm friends with this guy outside too. He's just going at it. All right, so take a look now. You see him? So here, this is the main sequence. Subgiants are over here, giants are over here, subgiants over here. And they just gave it some name. They said these guys are this classification. Like, let's see, like giants here. Look how much more luminous they are. Look at supergiants. They're so much bigger. The difference in sizes cannot be displayed here. Like if there was displayed, the supergiants would be as big as this entire page. That's how much bigger they are, like 1,000,000 times bigger than the sun, like that. Is that true? More than that, actually. They're huge. So that's what we're going to be working on. We're going to be working on what the heck happens to these stars. They all do the same thing. They burn hydrogen into helium, but then they freak out and they start evolving. And once they evolve, some of them become giants, some of them become super giants, some of them become subgiants, then some of them become white dwarfs, some become black holes. It's a whole story about life.
I guess I just don't understand the luminosity side of this graph.
Luminosity strictly means how much light you're putting out. So the luminosity versus temperature means if you have so much temperature, like if you have this much temperature, like 10,000 degrees, you'd be 100 times more luminous than the sun. That's all it means. Did you follow?
I did follow that.
You're
Okay.
worried about luminosity class still?
What?
You're going to be worried till the end of the semester if you're going to start worrying it. There's no reason to call it luminosity class 5. Some old astronomer decided to do it. That's all there is to it. Don't worry
Okay.
about reason for it. There's no reason they call it luminosity class 5.
Okay.
Okay, yeah. So
All
we
right.
call all the normal stars luminosity class 5s.